For today's lessons, let's talk about linear support vector machine. Before we talk about these problems, let's look at the dataset. So in here we have the relationship between the student GPA, which is represented by the left axis, x-axis representing the IQ of the student. And based on this dataset, we have two types of students. The blue one represents the not so good students, and the yellow one represents very good students. Is there any ways that we can separate the two types of data? We want to have some kinds of algorithm or models that can separate them. And if you look at these pictures right here, you are able to use a single straight lines to separate them. So by definitions, if any dataset that can be separated like this, we call this data linearly separable. But there's going to be a lot of ways that we can separate the data, and which one is the better one? So first, if we have a look at the model 1, which is the red functions, and the models 2, which is the green functions, they are able to distinguish the not so good students and the very small student. So how can we choose one? So which is the best model? So the main objective in SVM is to find the optimal hyperplane, which is this one and this one, in a multiple dimensional space, so that it can separate the data point in different classes in the feature space. For example, looking at the green line, we will try to measure the margin. It means the difference between this hyperplane and the nearest value. We're going to do the same for this one. And as we can see here, after we calculate the value and we sum it up everything in here, we will see that the green line, it has bigger margin, which is equals to a better model. But for the small margin, this red functions right here, the margin is not as big as this one. One of the things that you can see is we call this is an optimal hyperplane, which means that this is the best one and it will be better than this one. This is defined by two variables. This is the first variable, including the x feature. The second one is the bias. So using the weight and bias like this one, we'll be able to draw a line like this one. From that line, we can find the line that separates the data point by adding the value like this one. +1 and -1 equals to +1, -1 light right here. The way that we calculate the margin is we will use this function. We have number 2, and then we're going to divide it by the weight and the bias, and using this one we'll be able to calculate this one. After you have calculated, you will have the margin 1 and margin 2, and now it's just a simple task of comparing them together and see which line has a better margin, which equals to a better model. When we are doing mathematical modeling, is that our functions using the weight and the bias as the input, and we want to maximize this one. So how do we do that? There could be other like this one and other like this one equals to the green light right here, and we want these margins right here to be the highest. So that's why we have to define our objective functions like this one. The next thing we want to do is defining the constraint. We have the positive line, and we have, which we call the support vector, and we have the negative support vector, and this is our hyperplane right here. So the thing is, we don't want to have anything in this margin. So what we want to do, we add some types of constraint, meaning that the value can only be in this area, and it can only be in this area, and it cannot be here. And now we have this constraint, plugging this in the white function, and we have this constraint. In SVM, this is our primal problem. But the thing with primal problems is we will never be able to find the optimal hyperplane. So what we want to do is we transform the model into another kinds of problems through the dualities function. This means that we have two ways to describe the problems. In simple terms, for example, you have 2 minus 2 minus 2 equals to 6, right? So in dual problems, maybe we don't use this type of calculation, but we do something like this and says that it's gonna be faster for calculations. When working with primal problem and constraint programming, there's a lot of techniques. One of the most particular methods is the Lagrange multiplier. So it helps you to combine the objective and constraint together into another functions, and then we apply the KKT conditions, and after a few calculations we have another dual problems which is ready to be optimized. So why use dual form instead of primal form? As I mentioned before, the dual form is computationally more efficient than the primal form. So it comes particularly from the kernel tricks of the SVM, help us to handle nonlinear separable data by mapping the data from maybe 2D dimension space into another higher dimensional space in his 3D. Using the kernel trick. The next thing is we have a hyperplane, right? And we have some types of constraint. It means that there should be nothing between this one, but when you plot the models, it's gonna be impossible because this one and this one, when you use it with the models 1 or models 2, they're always gonna exist this value, and when you apply into the optimizer, some types of maximizer or minimizer, it will never give the result because it could never find a solution. Comparing to the hard margin, we introduce a new types of variables. We call it a slack variable. So in this one, even though I use this value, but it can be like the previous one, it can be wx and wb, then you'll see in this one. There are different ways to write this one. Objective functions and the constraints from the previous code is transformed into another one. So you can see here we have two new type of variables. This is the hyperparameters for our models to regulate. The next one is this one, the slack variable. For every value in the x function, add the slack variable to this one, and the constraint is a little bit relaxed. So basically it means that when we fit the light in the soft margin, we're able to let us have the noise exist inside the margin between the hyperplane and the negative and positive support vector. There are also other cases where this value is not supposed to be in these areas, but it still is, and by adding the slack variable. Now we look at the trade-off of the C hyperparameters. When we use the C equals to 1, the margin can be very big, and when we goes to C like 100, the margin is a little bit closer. And you can see some kind of trade-off where in here the models can be like about 70% accuracy, and in here 95% accuracy. In here it's a little bit overfitted because it tries to fit the data too much. So we want a little bit of balance between the two. Maybe it's 50 where we have a better value, like maybe around here, something like this is gonna be the normal trade-off.